Welcome back. In this lecture we're going to be looking at SYCL kernel functions, which represent the actual functions which are going to be compiled and invoked on your chosen SYCL device. But as a precursor to this, we're also going to be looking at the SYCL execution model and the ways in which it allows you to express parallelism in your applications. In this lecture we're going to cover the SYCL execution model, the SMT model for describing parallelism, how to define and invoke a SYCL kernel function, the rules and restrictions which apply to kernel functions, so you know what you can and can't use in a kernel, how to use both lambdas and function objects to define your kernels, and then finally we're going to cover how to manually compile a kernel function to give you a bit more control over how it's compiled. So we're going to start with the SYCL execution model. In SYCL, kernel functions are invoked on what are referred to as work items. You can think of a work item as a thread of execution. It will execute a kernel function from start to end. A work item can run on a CPU thread, a SIMD lane, a GPU thread, or any other kind of processing element. This depends on the kind of SYCL device that you're targeting. SYCL kernel functions are generally invoked on a number of work items in parallel, and these work items are grouped together into what is referred to as workgroups. The size of the workgroups is generally relative to what is optimal for the device that you're targeting, but can also be affected by the resources used by each work item. Choosing the best workgroup size is often a key optimization for SYCL applications, as it ensures optimal occupancy on the target device. The full iteration space that a SYCL kernel function is invoked over is described by what is referred to as an ND range, which means n-dimensional range. An ND range contains a number of workgroups, and each of those subsequently contains a number of work items. And the workgroups are always the same size, they always have the same number of work items each. An ND range describes a multidimensional iteration space, effectively how work items and workgroups are composed. An ND range can be 1, 2, or 3-dimensional. Here we have an example of a 2-dimensional ND range. An ND range has two main components to it. Firstly, there's the global range, which describes the total number of work items in each dimension. In this example, the global range is 12 by 12, so 12 work items in each dimension. Then there's the local range, which describes the number of work items per workgroup in each dimension. In this example, the local range is 4 by 4, so 4 work items in each dimension. So this gives us a total iteration space of 12 by 12 work items that's then equally subdivided into 4 by 4 workgroups. The global range must always be equally subdivisable by the local range.
When you enqueue a kernel function over an ND range, that function will be invoked exactly once per work item in the iteration space. Each invocation of the kernel function knows which work item it is on and can query information about its position in the ND range iteration space. Each work item has the following knowledge about its position in the ND range. Here we have an example to demonstrate this. First we have the global range. This is the total number of work items in the ND range in each dimension, in this case 12 by 12. Next we have the global ID. This is the index within the global range of the current work item, in this case the index 65, which is highlighted here in orange. Next we have the group range. This is the total number of work groups in the ND range in each dimension. In this case this is 3 by 3, as the ND range divides up evenly into 3 by 3 work groups. And the group ID, similarly, this is the index within the group range. In this case, the index 1, 1, highlighted here in yellow. Finally, we have the local range, which is the total number of work items per work group, in this case 4 by 4. And the local ID, which is the index within the local range of the current work item, in this case 2, 1, which is highlighted here in orange, relative to its work group, highlighted in yellow. One thing to note here is that different levels of this information will be provided to the kernel function depending on which API you use to enqueue your ND range. But we'll be covering these different APIs later on in this lecture. Typically, an ND range will be invoked over a very large number of work items. This can often be in the thousands. Multiple work items in an ND range will generally execute concurrently at any one time. And on vector hardware such as SIMD CPUs and GPUs, this is often in lockstep, which means single instructions spread across a number of work items. The number of work items that execute concurrently will vary from one device to another, and this can also vary depending on the resources used by each work item for the particular kernel. However, work items will be batched with other work items in the same workgroup, allowing for synchronization within a workgroup. But the order in which work items and workgroups are executed is implementation defined. The work items of a workgroup can be synchronized using a workgroup barrier. When triggered, a workgroup barrier will wait for all other work items in the same workgroup to reach that point before any of those work items are allowed to continue on. SYCL doesn't, however, support synchronization across all work items in an ND range. This means that workgroup barriers will not prevent adjacent work items in a different workgroup from progressing. The only way to achieve this is to split the computation into separate kernel functions and enqueue separate ND ranges. This is important to remember when sharing data between work items. Now we're going to take a look at the SMT Programming Model and what that means for how kernel functions are described in SYCL. So SIMT stands for Single Instruction Multiple Thread, and this is a paradigm that is used for expressing parallelism. To demonstrate this, let's look at two examples. In the first example on the left, we have a regular sequential CPU code. We have a function which takes an input pointer and an output pointer and loops over the pointers to compute some computation for 1024 iterations. In this case, the function describes exactly how the iteration space is traversed. In the example on the right, we have a function which takes again an input pointer and an output pointer, but also takes an index, and this function computes just the iteration for that specific index. We then invoke that function again for 1024 iterations, but this time by calling parallel for. Now in this example, the function describes only a single iteration, and the parallel for manages how the iteration space is traversed, allowing it to parallelize the computation. And this is how SYCL kernel functions are described, by defining a single iteration, which is then invoked for each iteration of an ND range. Now we're going to take a look at the different ways in which you can define a kernel function and enqueue an ND range in SYCL. SYCL kernel functions are defined and enqueued over an ND range by calling one of the various APIs. These are provided by the handler class available within the command group scope. These add a kernel function command to the current command group, and there can only be one kernel function command in each command group. In this example, we're calling one of the variants of the parallel for API. Now we're going to break down the different parts of this. The callable represents the kernel function itself, and this is the part which is compiled by the device compiler for the SYCL device that you're targeting. This can be either a lambda expression or a function object with a suitable function call operator. You may also notice that the parallel for function takes a template parameter. This is used to name the kernel function. This is important for pairing the kernel function across different host and device compilers. There are a number of different APIs for expressing different forms of parallelism, complexity, and functionality, depending on your use case. Each one takes the callable, but also takes some representation of the ND range. The callable also must take as a parameter a specific index type, which represents the current work item within the ND range's iteration space. And the type expected is relative to the API. In this case, we pass a range object, which represents the global range, and the callable takes an ID object, which represents the global ID within that range. These index types have a number of member functions for retrieving different information about the current iteration. There are three main ways to enqueue an ND range in SYCL. The first, in the top left there, is single task, which does as you might expect and invokes a kernel function exactly once. Single task doesn't take any range object, and the callable doesn't take any parameter. Next, in the bottom left, we have parallel for, which we've been looking at so far. There are a number of variants of parallel for, which we will cover in the next slide. Finally, we have hierarchical parallelism, which is split up into two APIs that are in the top right and bottom right, called parallel for workgroup and parallel for work item. Hierarchical parallelism represents the nested nature of SYCL workgroups and work items in a nesting of the two APIs. Parallel for workgroup is called first and is invoked per workgroup, and within that callable, you can then call parallel for work item, which is invoked once per work item. For this lecture, we're going to be focusing on parallel for, as this is the most common. There are three different variants of parallel for. The first takes a range object, which represents the global range, and the callable takes an ID, which represents the global ID within that range. In this variant, the local range is decided by the runtime. This is useful for when the kernel function doesn't need to know the size of the workgroup. The next takes a range object, again representing the global range, but in this case the callable takes an item object. The runtime still decides the local range, but the item object provides additional information. In addition to the global ID, it also provides the local ID, the global range, and the local range. This variant is useful for when you don't need to specify a specific local range, but the kernel function still needs to know what the local range is and the current work item's position in it. The final variant takes an ND range object, which represents both the global and local ranges, and the callable takes an ND item object. This variant is useful for when you need to specify the local range in order to ensure a specific workgroup size. All overloads of parallel for also take an optional ID object. This allows you to specify an offset. The offset, if used, will increment each index of the global range by the specified value in each dimension. So for example, if you have a one-dimensional range of 1024 and an offset of 512, then global IDs would now start at 512 rather than 0 and end at 1535. First, we're going to take a look at some of the rules that apply when defining kernel functions. Kernel functions can only be defined by a lambda expression or a function object. They can't be function pointers or std function objects. All variables captured in a lambda or stored in a function object must be by value, so they cannot be by reference. Kernel functions defined with a lambda expression must be named, and the name must be a forward declarable C++ type declared in a global scope. Lastly, kernel function names must follow ODR rules, which means you cannot have two kernels with the same name. This is important for using lambdas, as each lambda is unique and therefore needs a unique name. Now we're going to take a look at the restrictions which apply to kernel function code. These restrictions derive from limitations on what some hardware can do efficiently. Many heterogeneous architectures such as GPUs have less flexible control flow in order to provide higher parallelism and throughput. Some of these restrictions could potentially be loosened as heterogeneous architectures evolve in the future, so future iterations of SYCL may change. So you cannot do dynamic allocation in kernel functions, so memory must be allocated by the host application. You cannot do dynamic polymorphism in a kernel function, so virtual functions are not allowed. You also cannot call function pointers. Finally, you cannot have recursion, though template recursion is fine. Next, we're going to take a look at how to define kernel functions as function objects. So in all the examples we've looked at so far, we have used lambda expressions to define the kernel functions. Now we're going to look at how you can do this with a function object instead. A SYCL kernel function defined as a function object must store any variables such as accessors as member variables, and the function call operator must take the appropriate index type for the API you intend to pass the function object to. Remember, the member variables must always be stored by value. Here we have a full example of using a function object to define a SYCL kernel function. In the top right we have the function object we just defined, and on the left we have a simple vector add application now using the function object instead of a lambda expression. The parallel for is called as normal. However, before where we had a lambda expression, we now simply construct an instance of the function object type, initializing the accessors. Notice here that you now no longer need to pass a template parameter to name the kernel function. This is because the name of the function object type provides that name. Finally, we have the last topic in this lecture, precompiling SYCL kernel functions. This is useful for when you want to manually compile a kernel in order to have more control over how it is compiled. Generally, SYCL device compilers will produce binaries in an intermediate format such as SPEAR, SPEAR-V, or some other proprietary format. So when you enqueue a SYCL kernel function in your application, the SYCL runtime will often do just-in-time compilation to compile it down to the instruction set of the target device. This means that the first time you enqueue a kernel, it may take longer than subsequent enqueues. However, you can avoid this by precompiling your kernels. Precompiling kernels can also give you more control over how they're compiled, allowing you to specify specific flags or even linking other libraries. Here we have a simple application that we've seen before, and we're going to modify it to precompile the kernel in it. To do this, the first thing we have to do is to create a program object. Constructing a program object requires you to specify the context which you're compiling for. In this case, we're going to take the context from the queue that we enqueue the kernel to. Next, we need to compile the binary that contains the kernel. There are a few different ways that we can do this, but the simplest is to build it, which does both compilation and linking. We do this by calling the buildFromKernelType function, specifying the kernel name as a template parameter. You can optionally pass build options here as well, but in this case we don't provide any. If the kernel function was defined using a function object, we would use the function object type here. This has now done what the parallel for would have done implicitly. Now that the program is compiled, we have to retrieve the kernel itself. We do this by calling the getKernelMember function of the program object. Again, we specify the kernel name as a template parameter. This returns us a kernel object representing the specific kernel we want to enqueue. Finally, we call parallel for as normal, except now we pass in the kernel object as an additional parameter to instruct the runtime to use that instead of implicitly compiling one itself. We still need to define the kernel function so that the device compiler can compile it into an intermediate representation. This does feel a bit backwards in the flow of the application to be compiling the kernel before it's defined, however this is just an effect of the single source compilation.